Welcome to the Jack Westin MCAT podcast with your host, Phil Hawkins.
And Azaii Calderon-Muñiz. Hello. Welcome to another podcast episode with your two, we're going to choose to believe, favorite podcast hosts.
Your favorite MCAT podcast hosts. I think that's safe.
I hope that for someone, our shenanigans are truly their favorite.
Yeah.
But thank you guys for listening as always. So today we're going to have a top something. So we had a fantastic question come in. We had a couple of really great questions come in. And so we're highlighting a few of them during this podcast episode, part of the AMA series that we started a while back. And one of the things that among the list of many questions that folks had was about equations. And so that's something that we haven't talked a whole lot of before. And I know that sparked our interest, Phil. And so the question was about top 10 equations. We're not going to hold anyone to a number, but we're going to say top equations that you should know for the MCAT.
Yeah, this is something kind of like going through this. Like, honestly, we were going back and forth a lot, kind of like, okay, which kind of like focusing on like the highest yield stuff. And so kind of like looking back, like I have been going through the exams so many times recently from the AAMC because there's so many students who are taking the test soon. That like you kind of start to notice some things just tend to show up more than others. And like one of the themes that you're going to get kind of like from this equation list is energy. Like they love to ask about energy. And so this one, this is more of a unit than an equation of just knowing that like power is equal to work over time. Like power is measured in watts, and that's joules per second. And so if you have a 60-watt light bulb, that means that light bulb burns 60 joules every second. So it's a rate of energy expenditure. Now, I think a lot of times, like people kind of think like, oh, I have to use the equation for work or whatever to solve this. But really just any change in energy over time is going to be measured in watts. So like how much energy, like what's the power, the wattage of me climbing some stairs, right? Like what's the change in my potential energy? Divide that by how long it took me to do it. That's my wattage of climbing stairs. Or like powering, like, pedaling a bicycle, or like stretching a spring, or like putting two charges closer together. Like how much energy did that change and how long did it take me to do that? There's a certain power associated with that.
Yeah, you've touched on so many really important things, right? And like you mentioned at the very beginning, a pattern that you're going to notice and our listeners are going to notice is that it's related to energy. And part of this is because there are so many different ways that energy can come up on the exam. And there are so many different ways that we measure energy in life, not just on the exam. And so that makes it higher yield. Another way that this kind of energy component is being tested is directly with what is energy, what is the very basic equation for energy. And so you can be thinking about the force that you're going to exert. But if you just exert a force on a wall and nothing is happening, you're not doing a whole lot, right? And so you're not actually moving anything. It's the element of movement that becomes really important for energy expenditure when we're thinking about physics equations and we're thinking about the MCAT. And so in that case, you're going to think, okay, energy is the force that we are exerting over some distance that we move it. And that's going to be really important and part of this energy collection that you should have in your mind. I'm going to ask that when you finish this podcast episode, if you have a moment, jot things down. So jot down everything that you can think of associated with energy, every equation that we mentioned, and see what you can recall. We talked about recollection versus recognition in a prior podcast episode, but really try and be active during this podcast episode and after it as well.
Yeah, I think after we finish listing all these out, we should take a second and just list them all out again.
Yeah.
And so students can just write them all out. But yeah, so focusing a lot on energy, like power is work over time, energy is force times distance, or work is force times distance is often the way that it's kind of written. I do think like if there's one thing that is maybe even more important than like memorizing equations, it's units. Like if you know your units, that'll take you a long ways for a lot of these. So like powers in watts, energies in joules. So like if energy is force times distance, that means a joule is equal to a Newton times a meter. definitely want to know that. That's something that can just straight up give you the answer often. We all are obviously talking about like energy in kind of different forms. Not all of these equations have to do with energy, but like it's just something like it comes up so much because there's so many ways to change one type of energy to another and ways to connect things with that. And so it makes it easy for the MCAT to write questions. But I think maybe one of the most commonly used energy equations, just straight up, is just kinetic energy, where it's equal to 1/2 mv squared, m being the mass, v being the velocity, obviously. I actually find this equation more useful than all the kinematics equations, because there are some cases where you can't use the kinematics because kinematics require a constant acceleration. So like if you like have a spring and the more you stretch the spring, the harder you got to push, and like you like use a spring to push a ball or something, like as that spring changes distance, the force changes, which means the acceleration's changing, like as it's accelerating the ball or whatever. So you kind of can't use kinematics for those. And so there's a lot of scenarios where kinematics don't work. So if they ask you for velocity, what should be going through your head first off is, let me try kinetic energy, because there are cases where kinetic energy will work and kinematics won't. Any case that I've seen from the AAMC, if kinetic energy worked, then kinematics, or if kinematics would work, then kinetic energy would also work. So kinetic energy should be your default, because usually that can solve everything that kinematics can, and then some. It's also a lot easier of an equation than the kinematics, and so it's kind of an added bonus there. You get to, not that I'm encouraging laziness, but like if there's an equation that works more often and it's simpler, like let's use that one to start with.
It's something that you're going to have to do as a physician, in the sense that figure out, okay, what should my default for something be? Because if your default is a very uncommon illness, right, or something that doesn't always fit the script, so to speak, then it's going to be a lot more work, right? Whereas there often, if someone comes in with a cough and it is flu season, right? Chances are you're going to see a lot of flu. And then you're going to look for things that will point you in other directions. But to bring this back to the equations, right? Kinematics, it's kind of what you have to look for, because they're not going to work every single time. And making it your default is not the best use of your time. And so being good with time, being good with what you're focusing on, very useful for your future career as well.
Yeah.
So going on to our next equation, I'm realizing I think we didn't think we might have a bonus equation thrown in here.
We might, yes.
We might. So the next one is going to be that capacitance. And this one you and I were talking about, and you've been noticing this. And so you're welcome to chime in on this. So capacitance is going to be charge over the voltage. And so thinking about units, so that's going to be Faraday's for the capacitance, and then coulombs for charge voltage. Hope you know what the unit for that is.
Yeah. It's going to be volts.
Yeah, exactly. Volts. Yeah. And so you mentioned that this one, you noticed that comes up a little bit more than we might otherwise expect with capacitance. Yeah. And I know something that when I was studying was not on the top of my list. And so this is where using the data and patterns that you're noticing when you're completing questions to guide your studying is really important.
Yeah, I would say of all the circuit stuff, capacitors are probably the most complex and complicated kind of thing involved in that. And so the MCAT does, like if they want to ask a tricky question about circuits, they're probably going to come at this from an angle of capacitance. Now, the MCAT is more trying to test conceptual than like brute force math skills. And so this equation is a pretty simple one. Like capacitance is charge over voltage. And so like you can figure out what's the charge you can build up on a capacitor if you know the capacitance and the voltage, and kind of going through that. So the math is pretty simple using it, but it's still like a topic that generally causes students trouble. There are other equations for capacitance, right? Like it's the permittivity of free space times the area, cross-sectional area of your parallel plate capacitors divided by the distance between the plates. But the math there starts to get a little bit more complex. So I've noticed that they don't ask about that nearly as often as they do just charge over voltage is capacitance. It is kind of strange that like of all of the circuits questions, that might be the one that they ask the most questions about. It's also one that I think students like don't put much time in. And I think it's just because capacitors are complicated. But like having that equation there is something that it can be quite useful. There's also an equation for like the energy stored in a capacitor, but like 1/2 CV squared. That one also I think is not as high yield as just charge over voltage.
Yeah, this is not technically an equation, but being comfortable manipulating the numbers for parallel versus series circuits,
Yeah.
and being able to not just, because you're going to have to do 1 over a given number, right?
Mhm.
Depending on whether you're talking about the resistors or if you're talking about
Capacitors. Yeah.
capacitors, exactly. And so whether they're in series, whether they're in parallel. So make sure that you're comfortable manipulating numbers in that way and taking reciprocals, that 1 over, because you're going to need to do so on testing. I think a lot of times what can happen is we focus so much on trying to figure out, okay, what is 1 over this number, and lose sight of what can we do with all of these together in a way to manipulate the entire equation to make it easier for ourselves. So make sure that you have that down packed. That would be an unfortunate reason to lose a point on test day.
It is, yeah, just kind of overall, I would say of all the equations on our list, this one might be the one that students just literally are not studying and they should be. I think capacitors often go neglected, and there are some exams where you will have 2 or 3 questions just straight up on capacitors, and like this equation will come in very useful in those exams.
Yep. So
the next one was another circuits one, and that is V equals IR. This is just Ohm's law. This is your bread and butter circuits equation. Like if you're not dealing with capacitors, you're going to use this equation somewhere. Now, you might use some other equations in there as well, like finding the overall resistance of a circuit, or finding like, if it's an AC circuit, finding like what's the root mean square voltage and current, or things like that. But regardless, like often this equation, V equals IR, sometimes this is the only thing you need to answer a question. Sometimes it's this and then another equation kind of on top of it. But because of that, this one just shows up a lot. And they like to kind of like throw this and like understanding, well, once again, also just understanding like what is a voltage, right? Like everyone kind of has a good idea of like what a force is, right? Like I hit someone with a bat. They have an idea of what energy is, but like what's a voltage? Like what's an ohm? Right? Like the unit for resistance. I think students often have a harder time kind of wrapping their heads around those, like conceptually. And because the MCAT likes to go kind of conceptual sometimes, this is a topic that they can ask. Once again, note that the equation is not a particularly complicated one, right? It's not like a tricky math thing, but it's maybe just a little bit more kind of conceptual. I think that's a common thing that you guys might notice here, in that like we're not saying a lot of equations that are like, the Bernoulli's equation, which is like insanely long and complex. Because the MCAT is interested in more conceptual than math skills, the equations that tend to be the highest yield tend to not actually have that difficult of math involved in them. But yeah, that V equals IR, Ohm's law, it's a bread and butter one when it comes to like just dealing with circuits.
Yeah, what I found with circuits is, and I know I've mentioned this a number of times, equation sheets, I found them to be so incredibly helpful because there were so much going on with circuits when I was studying them. I was like, okay, there are a lot of moving parts, a lot going on. Even though the equations felt simple, right? It's like, okay, what does this actually mean? I found that having a diagram and having not just equation sheets, but also review sheets that let me see what was happening actually made it easier for me to understand and be able to tackle some of those more difficult questions. Not to give anything away, there are some questions that can be notoriously difficult on the MCAT related to circuits. And so making sure that you're comfortable with them conceptually, with the numbers, with manipulating the math and the information that you're given, knowing what information you actually need for a particular question is also helpful, because there'll be times that you're going to be given information either in a passage or that you don't actually need to answer the question. Don't try and force something into, that question that isn't necessary.
Yeah.
Okay. So the next equation that we were talking about is for the energy of a photon. And so that's going to be Planck's constant. So E energy equals Planck's constant times the frequency of a wave. And so this is another one that can seem very easy on the surface, but can become a little bit more difficult. There are some things that you need to have memorized for test day. This is one of them. And so making sure that you are able to keep track of these things is important. I don't think we've officially mentioned this. Make a review sheet, make an equation sheet, with the units as well as you're going through.
Yeah. Yeah. Make sure that you are definitely focusing on the units. I will say, of all the equations on this list, this might be the highest yield one, just E equals HF. It shows up a lot. And I think something that's really important for students to internalize is this is for the energy of a photon, not the energy of like a light bulb. If they ask you like, what's the energy going on in this light bulb? Like, I don't know how many photons are coming out of that. So just because you know the frequency of the photons coming out, that doesn't mean you know the energy of that light bulb. You would probably need to use something with circuits to find that, like find the power of that circuit and figure out the time. And that'll tell you how much energy, how many joules are emitted. That's actually using the power equals work over time or energy over time equation that we started this off with. But it is an important thing to keep in mind that energy of a photon is just Planck's constant, which is h times the frequency. I do also want to mention that the energy of photons is very tiny, right? If we're talking about the energy of a photon, using joules for that kind of doesn't make sense. And so often you'll see like smaller units, specifically electron volts. Like an electron volt is way, way smaller than a joule is. I think it's 1.6 times 10 to the minus 19th. Joules, you'll probably be given that on test day, like almost assuredly if they're going to ask you to do something with that. But like talking about the energy of a photon in joules, that's like asking somebody, how many tons do you weigh? Like, first off, that's rude. You shouldn't do that. Secondly, it's just the wrong scale. It's the wrong magnitude overall. And so talking about the energy of a photon in joules, like we tend not to see that. We tend to see things in electron volts or maybe even kilo electron volts. So you might have to do a conversion in there, converting the joules to electron volts or vice versa in order to use that equation. And that also comes up a fair amount. That like energy equation for a photon is, kind of sticking with the light kind of idea that we're dealing with. There's also the velocity, and this is of any wave. So the velocity of any wave is equal to just the wavelength times the frequency. Now, some waves have set speeds like light. And so you might see this as the speed of light equals wavelength times frequency. Note that the light is just a wave, and so velocity equals wavelength times frequency. So you can still use that equation for like sound waves or ocean waves, like crashing on the shore, people doing the wave in a stadium. You could use this. The velocity of a wave is wavelength times frequency. But you'll often see these last two equations combined, where you can use like C equals wavelength times frequency to find the frequency, and then you can plug that into E equals HF, or you could just combine the equations and like make it one equation rather than like multiple steps. So the equation would turn into E equals HC over wavelength. But both of these equations show up a lot. Like I said, these are probably in the running for if not, like probably the most high yield equations kind of overall in the totality of the exams that the AMC has released. And so you definitely want to make sure you know that. Note that light is very easy to connect to lots of topics, as light can knock electrons off of atoms. It can like knock electrons off our DNA and cause mutations. Like molecules can absorb light based on their wavelengths and frequencies. And so we can use this to like analyze like how much ATP is in this container because how much light is it absorbing, or figuring out the concentration of like DNA or enzymes or things like that. And so there's a lot of analytic techniques that are built around light, like UV vis spectroscopy, even mass spec. You can shoot a photon in and knock an electron off of things. And so there's a lot of things kind of going on with that. Not to mention like the decay stuff with like gamma waves and like surgeries and radiation therapies. Like note that light is radiation. So light kind of shows up all over the place, and it's very easy for them to connect it to a passage about cancer or analyzing glucose concentrations or whatever.
Yeah. And just a reminder, if it's being studied frequently, it's more likely to show up on the exam because the science experts, the science excerpts The passage excerpts, same with cars, are taken from pieces that actually exist. They were not written for the purposes of the MCAT. And so I think that point that you're making about, it could even be associated with cancer and radiation and whatnot makes it all the more likely that you can see it and that it can be brought up on testing. So you mentioned something about combining equations. So the next equation that we're going to be talking about can be rearranged and can be kind of has spin-offs, but it's the ideal gas law. And so the ideal gas law is that pressure times the volume of gas, and usually we're thinking about a container and we're thinking about balloons come up often, is equal to the number of moles times the temperature and the
Rydberg constant.
Yep, there we go, the constant. I was like, wait a second, why did I say temperature first? So PV equals nRT. There we go. And then keeping track of units, I think Celsius and Kelvin you want to be careful with. If I'm not mistaken, Kelvin should be your default for virtually everything on the MCAT, unless told otherwise, in terms of plugging into equations and whatnot. But that depends on the constant that you're using. So that's something to keep in mind as well. You can be asked questions about Charles' law, Boyle's law,
Avogadro's
Zach's law. Avogadro's law.
And
so, and so that you're going to want to be comfortable being able to manipulate the equation and knowing, okay, under constant pressure, under constant temperature, how would this be rewritten? What kinds of relationships can we draw if we have a situation where there's constant pressure? What does that tell us about the relationship between the volume and the temperature? If the temperature is constant, what does that tell us about the relationship between the pressure and the volume? And so even though you're not combining equations in this sense, you are manipulating the same equation to give you lots of different information and can be used in lots of different scenarios. We did end up doing a podcast episode on this. And so we recommend that you check it out if you're interested in learning more or hearing or just reviewing more about the ideal gas law. But it's one that I think is high yield because of all the different ways that it can be presented.
Yeah. I do want to mention, like, the ideal gas law, there's some assumptions. Like, we assume like the gas molecules don't interact with each other, like attract or repel each other, and that the atoms, like the molecules themselves, don't take up space. And that's why it's called the ideal gas law, because we're kind of like pretending, making some assumptions if they behave under ideal conditions. I've actually seen just as many, if not more, questions about what are the assumptions of the ideal gas law than I have of what is the, like, a calculation with the ideal gas law. I do think sometimes the MCAT also gives you, like, there's a shortcut, like any gas, if you have 1 mole of it, will be 22.4 liters at STP. So if you have standard temperatures and pressures. There is a van der Waals equation, which is actually a gas law that is not ideal, that is actually like incorporating those forces and the volumes. You might want to take a look at that. I don't think the MCAT's going to make you do a plug and chug with it, but make sure you kind of understand kind of what are the assumptions and how does this equation fix it. But that's also pretty, like, unlikely to show up compared to the ideal gas law. Since we're talking about the highest yield ones, definitely want to kind of like hammer that. On the temperature thing, like, generally you like stick with Kelvin unless it's a change in temperature, and then it doesn't matter, right? Like, because if I go up 10 Celsius, that's the same as going up 10 Kelvin. So there are some cases where like Celsius works if we're talking about a change in temperature, like Q equals MCAT, which is not on our list. But like, if you have delta T's anywhere, like Celsius or Kelvin doesn't make a difference. Fahrenheit will not work because a change in 9 Fahrenheit is a change of 5 in Celsius and Kelvin. And so that wouldn't work overall. But we have, I don't know if you guys caught this, but we kind of made this transition into chemistry, where the first several that we were talking through were much more physics-based ones. But the ideal gas law kind of marks a transition into kind of the chemistry side of things. Another really high yield one in chemistry is the Henderson-Hasselbalch equation, which is the pH is equal to the pKa plus the log of the conjugate base over acid. And I know that a lot of times students are kind of scared of logs, just overall, like, it's probably one of the most complicated math things you could have to do on the MCAT. But looking at this, I think the most important thing is to like recognize like how the ratio of the like conjugate base to acid, right? The acid has the hydrogens on it. The conjugate base, the hydrogens have fallen off. So like the deprotonated to the protonated state, understanding how that relates to the relationship between pH and pKa. So if your pH is below the pKa, you have more things that are protonated. If your pH is above the pKa, then it's going to be more deprotonated. And so you tend to have things more with more positive charges at lower pHs, because when you add H pluses to things, they tend to end up more positive. There are some exceptions, like a carboxylic acid, when protonated, is neutral, but when you deprotonate it, it's negative. So generally speaking, things are more negative at high pHs and more positive at low pHs, like comparatively between them. But just remember, low pH, protonated, high pH, deprotonated.
And this is not, what I'm going to say next is not technically an equation, but that becomes using that equation and knowing informally, right? Is it going to be protonated? Is it going to be deprotonated at a particular, I was going to say pH,
Yeah.
is important for amino acids. And if you have listened to virtually any of our podcast episodes, you know that amino acids are the single highest yield science topic, and you need to know them inside out. And so being comfortable with knowing, okay, is at a temperature, at a pH, goodness gracious, I don't know why I'm stuck on temperature, at a pH that is maybe not physiologic pH, will an amino acid be protonated or deprotonated? Will a chain of amino acids overall carry a positive, a negative, or a neutral charge? What will that charge be? And so being comfortable manipulating this and knowing the underlying principles that are represented with the Henderson-Hasselbalch equation are very, very important for testing.
Yeah, that's like, I like that you highlight that, because once again, this kind of like the stuff with the photons, this is important. Yes, I mean, it's like the MCAT wants you to kind of know stuff with this, but there's so many analytic techniques that are built around like charges and things like that. So note that like changing the pH of a gel can change the results of how your gel functions. Isoelectric focusing gels and like finding the PIs, like that is literally built around this, like low pH, high pH, what happens to the charge. It's also things like different types of chromatographies, where you could have like a cation exchange chromatography where your column grabs positively charged things. Note that under some conditions, amino acids will be positive and some negative based on their pKa's. I know everyone thinks about glutamic acid as a negatively charged amino acid, and that's because it is negatively charged at a pH of 7, but at a pH of 1, it's positively charged. And so a cation exchange chromatography would grab all amino acids because they're all positively charged at a pH of 1. And so being able to adjust the pH of like, oh, I want to like change the pH to get this column to let go of the glutamic acid, but hold on to everything else, right? Like all of a sudden there's some interesting analytic stuff you can do with this. And that's probably how the MCAT's going to approach this. Because that just kind of like connection overall. Yeah.
Oh, and say, I think this one actually marks 10, and then we hit the bonus. Please correct me if I'm wrong in the count. I think so. I was trying to count. So this next one is going to be, okay. So we're going to give you guys a bonus one in a moment. So the equilibrium constant, there are so many different ways that this can show up. But basically, you have a reaction, and you're going to have the equilibrium constant is essentially the product of the products over the reactants. So that's something that can show up not just with, combining two molecules or two compounds, I should say, to create something new, but even with things like enzymes. I remember getting so annoyed when there were so many different versions of KEQ, the equilibrium constant, showing up with the constant of binding and dissociation. It was like, oh my goodness. But it all follows the same principle of products over reactants. And this is a connecting point for something like stoichiometry and being able to balance equations. And here's a fun fact. Sometimes you just have to see if the numbers add up. And that can be a great way to get a question correct or and get that extra point. But it's at the intersection of a lot of different important topics. And so you will see it come up at least once in some version on test day. It's also the basis for when you think about equilibrium, right? What would happen if you had different conditions? And so what would kind of push a reaction towards or away from compared to its equilibrium,
Right.
what other conditions would impact it.
So like driving it forward or reverse with like Le
Exactly.
Chatelier's. Yeah.
Mhm. So this is going to be an important intersection that you need to be very aware of. And this is another situation where, like energy, I would just sit down and write down as many different versions of it as I could think of. And anytime it comes up, or a version of it comes up, write it down and have it all in one place so you can very quickly quiz yourself.
Yeah. Yeah. Like I often tell students that like the highest yield chemistry topic is equilibrium, and it is this equation that everything is built off of in that. And so I don't think we can overemphasize this, where like that KEQ is just telling you what's the balance of products divided by reactants at equilibrium. Like if you want a whole lot of products, then your KEQ is going to be big. If you want a whole lot of reactants, then its KEQ is going to be pretty small. So a bigger KEQ generally means the products are favored in this. And so I know you're talking about like all the different types of KEQs. Like in the course, I go off on a rant because this actually really does make me mad that there are so many types of KEQs.
I'm not the only.
Yeah. So like just in case you aren't aware, like types of KEQs, you have KAs for acid, KBs for bases, you have KW for the water ionization, autoionization, you have KSPs for solubilities, you have KDs for dissociation reactions, like an enzyme and substrate letting go of each other. You have KAs of association, which is a real pain in the butt because we already have a KA, right? Which is the acid one. But no, we also have a KA of association. I've seen K forward, K combustion, K reverse, like
KB for binding.
Yeah, KB for binding. Like literally there are dozens of these and they are all the exact same, right? The higher the number, the more it wants to go forward. And so this gets kind of like thrown in. I think one of the reasons this is so important is because of the connections to medicine. Like if you're looking at like an enzyme and a substrate or a receptor binding some new drug or something, you might look at what's the KD, which is how much do these things dissociate. And so a higher KD means it wants to dissociate. So that means it's binding worse. So a higher KD means your drug is not going to bind as well. So it's a worse drug. A lower KD means it's better. And so they will straight up just give you tables of KDs or KAs of association, which are just the opposite. And I want to remind you that's not the same thing as a KA of an acid. And it just like drives me nuts because they're literally all the same thing. But they just have different names.
I don't think I had ever seen you express what I feel inside about KEQ until this moment. Oh,
I don't think I even mentioned solubility product, KSP, and like that's a big one. And like it's just all over the place. And I think the real reason I'm frustrated is because I didn't realize they were all the same thing when I was an undergrad, and I like learned it every year, like in a different context. And then all of a sudden, like, wait, this is all the same thing, and nobody told me. And like, maybe it's on me, and I just didn't pay attention. But I'm still mad about it.
Very fair. Do you want to give us the last?
So the last one's just, once again, kind of thinking about like reactions and kind of stuff happening. This also has a lot of interplay with metabolism, and that's just thermodynamics. Like, does stuff want to happen? Or am I going to need to put in energy to drive stuff? And so delta G's, right? Your Gibbs free energy. If that's a negative, it's a spontaneous reaction. If it's positive, it's going to be non-spontaneous, and it's going to be hard to get that to go forward. But the equation for delta G is just delta H minus T delta S, where delta H is the enthalpy, which is the energy inside the molecules, and the delta S is the entropy change over the course of the reaction, where entropy is disorder. Generally speaking, I like to talk about this conceptually with students. Things want to lower the energy. Like that makes sense. We want to be low energy. We want to be stable. So a negative delta H means the energy is dropping. And so that drives the reaction forward. Also, things want to break down, right? They want to like break apart into pieces. Like if I took like a Lego house that I built and stuck it in a pillowcase and then shook it around, like it's going to fall apart, right? I can't put a bunch of individual Legos, shake it around and have a house come out of it because things want to break down. And so the delta S, when the entropy is increasing, when the disorder is increasing, that also drives it forward. And so a lot of times they'll ask you calculation questions of like, should you, or like, what's going on with the delta G? Is this spontaneous or not? But they might also just ask a question about like, they'll give you the delta H and then ask about the like beta oxidation. what's going on with that. And they'll expect you to know, well, when you break down like carbohydrate or not carbohydrates, when you break down fatty acids, you make smaller products. And so you're going to be increasing the entropy. And so without giving you a number, you're going to have to be able to know that the delta S is going to be positive for that. And so they like to kind of take that and combine it specifically to metabolism, and under like what conditions this would want to go forward or not. And also how that interplays with temperature and like reactions in a test tube. And there's just so much stuff you can connect that to.
Yeah. And to go off of that, that should hopefully have made some of you think, oh, so I can answer some questions just by knowing the signs.
Yeah.
Yes.
Yes.
There are some combinations, right? If you think about it, if one of them is positive, the other one's negative, depending on which one's positive, which one's negative, you might know for a fact that it's going to be a spontaneous reaction. You might know for a fact that it's going to be non-spontaneous. And so what I liked doing and what I always had my students do when we were going through this was to have like a 2x2 table of when enthalpy is positive, when enthalpy is negative, when entropy is positive, when entropy is negative, and write down under what conditions will it always be spontaneous, under what conditions will it always be non-spontaneous, and for the others, what would kind of have to be the ratio. So would one have to be much, much, much bigger, right? Obviously accounting for the fact that we don't have the temperature, but nonetheless still being able to think about it. And so that can be very helpful on testing, because if you see, oh, positive, bam, is not spontaneous, right?
Yeah. And like, you can just sometimes just get down, even if you don't know the exact answer, like sometimes you can get to just like the answer's A because that's the only one. But a lot of times you can even get down to a 50-50 right off the bat without
better than 25%.
Yeah, without doing any kind of math. Just like the equation itself, right? Like, so if one thing's pushing one way and one's pushing the other, like which one wins, right? If enthalpy wants to go forward and entropy doesn't, who wins in that case? That's when we care about the temperature, because note that the temperature gets multiplied by the disorder. And so at low temperatures, the disorder is the less important thing. At high temperatures, it's the more important thing. Kind of figuring out like what's more important, the energy or the fact that we want to break down into more complex stuff. So the equation, let's just like run through real quick. This equation list, which is 10 plus 1 bonus 1 that we definitely did not realize there was 11 until we started the podcast. We just got so into it, we kept writing. But so equation, the first one is power is equal to work over time. Second one is energy is equal to force times distance. Kinetic energy is 1/2 mv squared. Capacitance is charge over voltage. The voltage is equal to current times resistance. That's our Ohm's law. The energy of a photon is Planck's constant h times the frequency. The velocity of a wave is equal to wavelength times frequency. We have the ideal gas law, which is PV equals nRT. Then we have the Henderson-Hasselbalch equation, which says pH is equal to pKa plus the log of conjugate base over acid. The big takeaway there is low pH is protonated, high pH is deprotonated. Then you have KEQ is the concentration of products over reactants. I don't think we mentioned this, but it's just the aqueous and the gaseous stuff. Yeah, we leave out liquids and solids and that. And that's actually a pretty important thing that we probably should have mentioned. But like, at least we mentioned it now. And then the last bonus one is delta G is equal to delta H minus T delta S. And I would say those 11 equations are probably the highest yield ones, period, on the MCAT. Note that I know we kind of talked like chemistry and physics. There are equations in biology with like Hardy-Weinberg equilibrium and like enzymatics stuff. There's even stuff in psych with like Weber's law. But most of the time, if you're doing something with an equation, it's going to be a chem phys thing. And so those equations are the ones that I think are the most important overall.
Yeah, very much inclined to agree with you, Phil. Mm-hmm. So we have two other more personal questions that we got asked that we're happy to answer. I can take the first one. So a student mentioned that they asked and they're curious about the best and worst part about studying at Harvard for medical school, and that they, like Jack Weston, want to find a medical school that's similar in structure. So I think if you're thinking about structure, you want to learn more about the programs themselves. The best and worst part, you put me in a tough situation with that worst part question. Yeah. But I think the people have a lot to do with the experience. And so I don't want to discount the effect that not just the administration has on your experience as a medical student, but also your peers. because I can tell you right off the bat. So at HMS, when I started, part of the reason why I came to HMS was because of my potential future classmates. When I went back to revisit and I met some people that I eventually became really great friends with, that was a huge draw to going to HMS. And so arguably that would be the best part of the experience, the connections that I made, the people that I formed friendships with, the people that I learned alongside with and learned from, that it helped me through all my mad moments. And we had mad moments together, mad, not necessarily being angry, but just shenanigans, confusion, stress, chaos, wild, fun, you name it. And being with them helped me learn a bit more about balance and what I was and was not looking for long-term in my life, right? What kind of future physician do I want to be? I'm going to learn just as much from the people that I'm surrounded by as I am from what I learn in a classroom and the content. Because I came into medical school. At one point, when I was little, I wanted to be a surgeon. I don't know who thought it. My parents should not have let me watch. It was called like My Life in the ER, Life in the ER, something like that. Yeah. Did you ever see it, Phil?
No, but I feel like I've seen similar shows, even if I haven't seen that, of just like ER. Yeah,
it's like actual stories from the ER. So I thought I wanted to be a trauma, cardiothoracic neurosurgeon. Obviously, that's not going to happen.
Yeah.
And then I did hemonc research in undergrad, and I was like, okay, so I'm going to be a hematologist, oncologist, and then I was like, I'm going to be a cardiologist, and all these different things. And what I learned in the classroom was not what ultimately helped me decide, yes, that's what I want to do, or no, that's not what I want to do. So I would say the best part is the people that you're learning with, from, and alongside, and then also patience. Make sure that when you're deciding between medical schools, look at what kind of mission they have and where you would be learning and what types of patient populations you would be learning with and from. Right. And I'm saying learning from because you learn from your patients. You don't just learn by practicing, with patients. Anyway, okay, going off on a bit of a tangent there. I will also say for me personally, going to a school that was pass-fail preclinical was also incredibly important for my experience. And I do think, and this might be subjective, but I think that contributed to people being comfortable helping each other and really working together. Like, okay, we have this exam coming up. Let's all share notes. Let's sit down. Let's study together. And I would add that to being a positive part of, a Harvard med experience, HMS experience. I think that transition between undergrad and medical school can be an incredibly intense one. And anything you can do when you're thinking about the future structure of the schools that you're looking at, making sure that you have that collaborative environment. And so you mentioned that, you really like things at Jack Westin. That's something that I absolutely love about our students, is the way that they support each other. And so, doing sessions in the course, seeing the way, if I don't get to a question fast enough, students are responding to each other in the support, in the chat, where they're saying, I'm going through that too, or you're not alone, or me too, and just kind of brainstorming together. And I do think that a pass-fail preclinical curriculum can contribute to that kind of environment. Also seeing, is it just lectures and massive groups, and it's just a group of 150 students all learning in one classroom at the same time or not? You're going to have, if you're thinking about, your experience at Jack Westin versus that's going to be very different, because the instructors are not going to have the capacity to get to know 150 students in one lecture hall, right? If that's all that they're ever interacting with y'all with. So at HMS, one of the things that they do is that they break up a class into societies, into smaller groups. And I know a number of medical schools do this as well. And so the students get to know each other a little bit better. You're with them for longer periods. The instructors get to know the students better. I almost don't want to answer that because this is recorded and on the internet. But I think this is something that can be true for any medical school and for just about any experience. It is, administration will not always have all the answers. And people are human and they make mistakes and people disagree. And you may not agree with decisions that other people are making, how problems are handled. And that has been a point of tension for me personally, just because there are things I would handle differently. And we can't change other people's decisions, and recognizing that we live in, and we study in an ecosystem where there are a lot of moving parts and people have different pressures. People have, there's just a lot that goes into it. And I would say that as a way to buffer some of that, is when you're interviewing for medical schools, ask them how they keep their students in the know. Meaning, okay, for something as simple as scheduling, right? This is something I've actually heard from students at other med schools, that they don't find out their schedule until super last minute. They don't know what they're rotating on until just right before the rotation, right? That's something that I will say is not as much of an issue at HMS. They actually do a pretty decent job of, where you're going when. But something as simple as that can have a huge impact on your experience and can turn something that could otherwise be really positive into something very sour. So ask questions about that. Ask questions about, okay, when was the last time that your administration implemented student feedback and what was it, right? That shows you how responsive they are, how much they're willing to work with you, et cetera. So a lot there.
Yeah.
Unpack it as you will. But it sounds like if you're enjoying the Jack Westin structure, really, you want to know how the administration and the instructors are invested in students at the end of the day.
Yeah. I will say, I know this was like a question for you specifically, Zai, but I do want to echo a lot of the things you were saying. Like for me, the best part was the people, like the peers and kind of going through that. I also can like very clearly kind of understand. I feel like there's a lot of like people who are in med school tend to be very driven and hardworking and capable individuals. And what I found is a lot of the administration kind of just is like not as supportive because they're just assuming that like things are being taken care of. And if you need something, you'll kind of address things. And like often there's less like structure built in there for support because they're just kind of like making assumptions and it's just there. Not that like anybody should feel bad if they need support because going through med school is incredibly complex. But I tend to feel like sometimes that support is lacking. I felt that as well a little bit when I was in med school myself. Kind of in hindsight, I'm like, oh, I should have been more proactive hunting those things down. But like, I just feel like it wasn't an easy system to get that support because it wasn't super clear. But maybe my thing was a little bit different than yours. I do want to say I like the working together and team kind of stuff. I didn't go to Harvard. I went to the University of Nebraska, and our school wasn't pass fail, but like still there was a lot of kind of like working together and kind of sharing notes and things like that. But I am kind of curious because you guys did a lot more clinical stuff very early on. And I really wish that my school would have done that because the first 2 years, we essentially were just like sitting in the basement with books. And I kind of needed that patient interaction to help keep me motivated, to remind myself that what I'm going through with med school is not that I want to study nonstop, but that I want to actually be helping patients. And so, that's something when I like hear about kind of like the way that Harvard does things, I'm like, ooh, like I wish that I had more patient interaction earlier on. And I think that would have made my experience a lot easier, if nothing else, just to help keep me motivated, because it is very much a grind getting through med school. And I know that like if you'd asked me like, Phil, would you want extra assignments to go do clinical stuff? I know I would have absolutely have said no because I don't want any extra stuff because there's too much stuff already. But on the other hand, I think that I actually would have benefited and flourished a little bit more in that sort of environment.
Yeah, it's a bit of a double-edged sword because on the one hand, I actually wish that I would have had more preclinical time. So even in the preclinical time, in the first year and a half, we were still seeing patients. We had, I believe it was Wednesday mornings. I want to say we were in clinic and seeing folks who practiced interviewing, things like that. And that was incredibly helpful. And I do think that was an integral part of the learning experience. My frustration when we moved into primary clinical things so quickly was I felt like I didn't know enough when I went into the hospital, when I went into, being right there all the time, helping learn and provide clinical care to the degree that I understood. And it was a much sharper learning curve that I think would have been helped if I had had more of that content knowledge and better understood that. That said, I think the way that I interacted with patients and the medical ecosystem benefited from being able to do that, transition into that full time, so to speak, earlier on. And so I think it has its pros and its cons, but it's definitely something to look at when you're applying to medical schools because, for you, sounds like that would have been a slam dunk, definitely the way to go. For me, it's like not 100% sure. And there are probably going to be other folks that are like, I need more study time for maybe, you're thinking about less clinically involved work after graduating medical school. And so that can also be something that, will affect your experience and goes into consideration.
Yeah. So there is one other question that we got, that this is actually one that is very not MCAT related, not med school related, but I mentioned in one of the podcast episodes something about a date I went on with that had something to do with candied ginger. And so some students have asked about it. So I'm like, okay, we should talk about it, just because I had kind of like dropped hints. And I think I said if people asked, I would talk about it. So we should talk about it. I am happily involved in a relationship now, but there was a point where I was doing some like online dating, and I was like chatting with this person, and they said that they were very into nutrition. And I'm like, oh, that's cool. Like, they knew that I went to med school and was very into science, and like I taught science stuff all the time. And I'm like, oh, okay, there's a connection there, because like nutrition and like talking about like what happens in like late starvation versus early starvation, and like building and how we break down stuff and like the metabolism. Like, oh, that's kind of an interesting thing. I like to talk about that and think about it. And so I went on this date, and it was a first date, and I asked her like what sort of nutrition stuff is she kind of interested in. And she started this, and my like I immediately, the mood kind of darkened in my head. I'm like, oh, okay, this is not gonna go well. But she was saying how she had just recently discovered the healing powers of crystallized ginger. And I'm like, oh, okay, like I want to hear more, but like my defenses just kind of went up a little bit. I'm like, okay, hang on. And then she expressed to me that she just cured her grandmother of diabetes using crystallized ginger. And so this is when I stopped, and I'm like, wait a minute. Do you mean like crystallized like candied ginger? And she's like, yeah, don't worry, like it's irradiated, so it's fine though. And like there, like in my mind, there's like multiple things going off, and like thing number one is I'm like, okay, hang on, but like she's like very clear, like there was no radiation involved, and that's what makes it okay. And like a part of me is like, light is radiation. So somehow you grew this ginger without light. Like that is a miracle of photosynthesis. I don't know how you did that. Secondly, you're feeding sugar to a diabetic to cure them of their diabetes. And I'm like, you got to immediately stop doing that. And like she had got her grandmother to stop taking like her diabetes medication because the ginger was going to cure this. And I'm like, okay. I was like, there's some problems here, but like, okay, this probably isn't going to be a second date, but you should definitely not be doing that. And going into this, yeah, that date did not go super well. And that was like the first date that I had been on in like 3 or 4 years. And I'm like, okay, this dating world is like, I don't know if I'm okay with this, and like kind of what's going on in the world there. But yeah, that was it was a first date over many years. I'm like, okay, this was not, this is not what I was expecting and kind of hoping for.
Good on you for not disappearing altogether from the feed.
Yeah.
Because I think I would have just dipped after. I would be like, all right, we're done with all of this.
Yeah.
More.
The medicine side of things and like the physics. I'm like, first off, you didn't do that. But like radiation, you know what that, like that's photons, that's light. And I'm like, yeah. Anyway.
Oh my goodness. The stories we could tell, the stories you could tell.
Yeah, that date did not go well. But
really enjoyed this. I really enjoyed this. Just giving a couple of equations, giving some fun stories. Thank you guys for listening and for being a part of the Jack Westin MCAT podcast with us.
Yeah.